I want to share some footage from a recent project of ours, the DARPA Subterranean Challenge that Marco just referred to. The goal of the challenge was to develop robotic teams that could explore natural and built underground environments, such as tunnels, caves, mines, urban settings like subway systems, in order to find objects of interest known as artifacts in the challenge and build maps of the environment. Implicitly, this was a multi-robot coordination challenge and also a human-robot interaction one as a supplementary component. I'll talk a little bit about that. And the challenge started in 2018 when we were selected for funding as part of the competition by DARPA. And we had about a year to go from having no coordination between the PI team and our groups, research groups. There were 4 of us, and having to spin up essentially a fully staffed $1.5 million year operation to serve the project. Very few PhD students were interested. I'm sure some of you can imagine why that would be. We had a core group of students who were very intrigued by the challenge, though, and the competition made up the bulk of their PhDs as they were completing the project. There were 3 competition deployments, originally scheduled to be 4, but because of COVID, only 3. The first was in a limestone mine in Pittsburgh. The second one was in an abandoned nuclear power plant outside of Olympia, Washington. And the final event was in an underground constructed course incorporating elements of various different types of challenge environments from the previous stages in the middle of Louisville, Kentucky's mega caverns, which is essentially an enormous underground cave and tunnel system. So this is just some footage as people are trying to get themselves sort of like situated in what's going on with this project. So the finals course, as I was mentioning, was quite challenging. The scale of the course was enormous for many robotic deployments, with large caves augmented into the constructed course and narrow caverns with challenging terrain elements strewn about by DARPA, such as these rails here, which were basically meant to stop any tracked or wheeled robots that were trying to go over them. And on the left, an enormous cave that had to be explored in its entirety of volume because they could have put an artifact basically anywhere. And to live up to their tagline of DARPA hard, is a term that's frequently used by DARPA projects, the competition included a fully constructed subway system, including a ticketing station, platform, subway rails, tunnel about 100 meters in length inside of it. Really a fun course to have to walk through at the end of it. As I mentioned, there was an HRI, human-robot interaction component of this project. Where did that live? It was with this single human supervisor here wearing an orange helmet. That was the only individual that was on the team who could actually interact with the robots once they were past the starting gate. And the interface here of how the supervisor would interact with the robots was up to them, as was how the interface would actually communicate with the robots. So this was really our project to build from the ground up, interfacing with the DARPA systems and how we go into the mine. We had 15 minutes to set up the system. It was supposed to simulate what was kind of like a real-world disaster scenario or disaster response scenario. And this person, with all of what you saw here, was everything that was possible after that 15 minutes. So here I show a few photos from the final event just to give you more montage kind of background here. Consisted of constant testing at the event, team meetings, live discussion with other teams, because this was a group of us plus 7 other teams that were there from all over the world competing. And at the conclusion of the competition, our team finished 3rd place globally and is the top American-led team, eking out a win over teams led by JPL and CMU, but placing behind teams that were from an international constituency, Norwegian Technical, ETH Zurich, and the Australian CSIRO. So we were able to walk through the course afterwards and observe, like I mentioned, what we had missed in the enormity of this built structure that DARPA had. So that's that one little vent right there, which was one of the artifacts that we were looking for. And that was after the competition was over, we could do this quick walkthrough. And like I mentioned, we scored 3rd place, which meant that we took home $500,000, which has been used to support our research groups continuously. So with that introduction aside, I want to talk a little bit more about what our team's solution was, how it evolved over time, why we had an eye for radar-based perception in this challenge, and maybe some next steps or where we would take this going forward. So first, I want to say our team was fairly large for most research projects. One might imagine it to be quite large. And by that I mean this is a group of almost entirely PhD students with a few undergraduates, broken up into sort of their different spheres of influence in the project. As you can see, we had a team that was specifically focused on platforms. We had another team that was specifically focused on building out all the autonomy components, including perception components and planning and decision making. We actually had to set up our own comms system, as I mentioned, inside the caves that were basically RF absorbing. So we had a dedicated communications team for that. And we had a management team, which I'll talk about a little bit, not just PIs, but also some graduate students that we sort of elevated to the position of project engineer to provide extra management. So today I'm going to focus mostly on platforms and autonomy, and I won't be able to talk about our comms solution. It was very interesting, and if you're interested in more of how that was, we actually have a field robotics journal paper that just came out, which you can read more about how that worked. In case you're wondering why I highlighted some students' names, those are the students in my research group, those names that are in red. OK, so let's jump into platforms to talk about our evolution of platform decisions, which I think is a nice microcosm for how these challenges work and, in some sense, how we might think about deploying robotic solutions into the wild. So when one ends up with a research project like this, one typically is faced with a decision about how to start and what is the easiest thing to start with. Mostly the platforms you have sitting around the lab, am I right? So if that's the case, then you sort of look around and you say, well, we have some Huskies, and previously my work has done some research in this 1/8 scale RC car kind of world. And so these two platforms were meant for very different tasks. On the right-hand side, this parkour car, we idealized as a robot with a mobile comm relay. So that would be that it would just be sending signals back and forth between these Huskies, which were the ones that were essentially doing all of the object detection or artifact identification, as well as mapping, high-definition mapping. So the Huskies, what I'm going to focus on in this conversation, our tunnel configuration, which was the first configuration we deployed, featured a similar sensor post to what we actually ended up with in the final competition. It had some evolution on it, and I'll focus on that in a little bit. But it was outfitted with a OS1 64-channel LiDAR right on top, as you'll probably see in almost all robot designs. The robot LiDAR is typically the highest sensor in the platform. An Intel RealSense D435 array, so you can see 4 D435s, 2 facing forward, 2 facing sort of obliquely to the side. What is not pictured here, though, is a drip shielding. So just when you thought Pittsburgh weather was bad enough, it actually rains in caves there, which we found out when we deployed to Pittsburgh. So there was rain everywhere, even underground. It's horrible. So the challenges we saw from this particular setup were that, for instance, on the right-hand side, this parkour car, it's an Ackerman steering vehicle. If you don't know what that means, it's basically that it has to back up in order to make certain types of turns, 3-point turns, 5-point turns. This creates an enormous challenge for planning, but also is not great for narrow corridors. I don't even know what we were thinking when we thought we would field this thing, because the narrow corridors made it so you basically must be correct in how you're aiming against the walls. Not easy. And so we thought that this thing would give us a bunch of speed improvements, but in fact, the speed that the car gave was never realized because a single false move would be catastrophic. So we basically just crawled it forward. In fact, nobody moved very quickly at tunnel, and I would argue no one really moved fast anywhere, which brings me to one of the conclusions I think I want to bring out firsthand, which is that reliability is extremely important in almost all robotic deployments in the wild. And if speed is part of your sales pitch or what you're trying to do in your team, then you're going to have a really hard time with that, because speed sort of increases the lack of reliability that any one of your other sort of components might have in it. In fact, this lesson was, I think, learned gradually by all of us throughout the program. Nobody actually moved fast by the end of the program. Everything was moving at most 1 meter a second. And so that's a little bit of one of those things that I want to get to, the conclusion about where I think things could go looking forward. But next, I'm going to just say, what was our urban configuration? This is the next competition event. So on the top right, I show this little graph where it's tunnel was the first event, urban was the next event. So urban's the next evolution of our systems. And we did pretty well at tunnel. We actually placed I think we tied for third or something. We did fairly well, and we thought, okay, if we have a good standard or foundation, we're going to expand on that. So we decided to ditch the fixed multi-real sense camera configuration used for artifact detection. And instead, what we decided to do was put a single real sense on a pan tilt unit so that it could look around. One of the things we saw was that this multi-real sense configuration did a couple of different things. One of them is that if you have a bunch of USB vision cameras hooked up with USB 3 to a computer, very frequently you end up with bandwidth issues. If one USB camera falls off because of a bandwidth issue, it actually can take down the entire USB controller, which means you no longer have any vision, which would have meant that our platforms are useless in the cave. Okay, so that was not acceptable. We decided to go to one real sense. But obviously, one real sense can only look in a very narrow field of view, so we thought, why not put it on a pan tilt? That was a terrible idea, and I'll get to why. Okay, so we had that configuration. We also added a few different drivetrains here. We said we're going to replicate what we did at the Husky and put it on these tracked vehicles. Justification for that? Well, if we're going into urban environments, we have to go upstairs, and wheeled vehicles can't easily go upstairs. Boston Dynamics hadn't begun selling their Spot robot at the time. If you wanted some sort of quadruped, you would have had to build it yourself. And if you do it just right, then these tracked vehicles or tracked vehicles plus some flippers can actually go upstairs. Okay, so we thought that's going to solve the stair problem. We complemented it with actually a smaller vehicle called the LT2. Also had the pan tilt configuration, basically just a smaller version of the tracked vehicle. And we added a UAV on just because we thought we had more time and not enough difficulty already. So altogether, we felt that this simplified our solution, right? We eliminated some of our real senses. We decided to replicate the Husky platform onto the tracked vehicle platform. Who thinks that this looks like it's simplifying? I'm sure nobody in this room. Okay, so in reality, this was actually like a disaster at Urban, and I want to focus in on why. So even though we had made some substitutions, we, for instance, decided, okay, we're going to use a pan tilt. There were a lot of challenges with this particular type of fleet loadout. So tracked vehicles required completely different terrain classification systems that would be built around basically what their new high center position would be. They would high center everywhere. They actually just got stuck on even small steps. When I mean high centering, that means you can't move after it because you have some contact condition that's no longer satisfied for your drivetrain. The pan tilt unit that we had, because it was using a pan tilt, it would actually have encoders in it to determine where it was looking at any given time. Encoder failures would result in our not knowing what we were looking at, even if we had a camera that was giving us imagery. So we couldn't project where these artifacts were into the frame of reference of the robot because you had these encoder failures. So what did we do? We did what many engineers make the mistake of, replacing a multi-point of failure system with a single point of failure one, which actually doesn't really help you because if you have that single point of failure hit, then essentially you have decided, then your system no longer works. Okay, the UAV actually worked pretty well, but needed twice as long as we had given it for development time, so we ended up scrapping it for the deployment. Just a bunch of different issues associated with that. So basically, the summation of this was at Urban, we tried with the 3 self-funded teams and placed last with respect to all the DARPA-funded teams. And this was an absolute low point of our morale. And what would you have it? COVID happened 1.5 months later, so we couldn't even meet to work on the platforms to debrief. Some of us talked about pulling out of the competition. I mean, what are we going to do? We all really took a step back and started having just a bunch of, as we all did during that time, Zoom meetings to figure out what was our next step. How are we going to respond to this setback at Urban? So I think COVID was a real reset for us. And some of my conversations today have focused on identifying crises for what they are. I think the pandemic really changed how we did work, both from this perspective, but also graduate school in general. I think many of us can understand what I mean by that. And the team decided to have 2 graduate students instead as a response to our failure at Urban take on what I mentioned as project engineer responsibilities or leadership at par, if not above, the PIs on the project. And there were a lot of reasons for that. But I would say I would attribute our final win at final to them. I think they probably worked like 80-hour weeks, but also they were very willing to tell us when something was not reasonable or when people had questions that they weren't willing to raise to us. But I'll talk about that in just another slide in a sec. Our final loadout, just to talk about what you see on this slide, is this. So we ended up with a ClearPath Husky, same as before, tried and true. You'll notice that we don't have any tracked vehicles because tracked vehicles, as I mentioned, are super challenging in a terrain categorization setting. The compute stack was left largely unchanged. A few sensors were removed, so we actually removed flash lidars from our setting. And what we did was we replaced all of our cameras with gigabit Ethernet cameras, and we decided to put 4 of them back on there. Gigabit Ethernet is amazing. If you've never worked with Gig-E Vision before, I strongly recommend it. What happens when you drop a frame in Gig-E? Nothing. You just don't get the frame. The next frame will come within the next 1/30th of a second. It's awesome. We had completely reworked our beacon deployment mechanism as well as the infrastructure supporting the networking. 6 beacons per Husky rather than like the 24 you saw before. We realized we didn't need that many. And we purchased 2 spot platforms. They finally went on sale, and we were able to get 2 of them. And so what did this give us? Well, it supported our not having the track vehicle anymore, because now we could go upstairs, and Boston Dynamics engineered the hell out of the stair climbing capability on this spot. The black box attached to this spot here is actually almost the same as what's inside the Husky, but with a few years extra of development of hardware, that's what we were able to miniaturize it down to. And we even were able to put a small GPU inside of it for artifact detection on computer vision, which was, again, the purpose of the challenge. And the use of the spot allowed us to traverse more tortuous terrain, travel twice as fast as the Huskies or any other platform we had seen before, travel up and down stairs. It was really a true game changer. I think that many people realized after Urban, when one team successfully fielded a spot, the JPL team, who had somehow gotten their hands on a spot earlier than anybody else, that quadrupeds were the solution to this challenge. It might seem like wheeled vehicles would be, but in fact, even with really bad terrain, this spot could be able to handle it. So this was just a couple of takeaways, I think. The conclusions from this was that I think some features are conditioned on deep design choices is not really an obvious finding or conclusion. So one of these issues was that we couldn't deploy a UAV off of the Husky. And the reason for that was that every time we wanted to do mapping and localization, that would have to start from the gate and have to be surveyed into the gate. There was no way to serialize the state of any one of our robots and then transmit that to another robot. And that was actually a design choice that was necessitated by using ROS. And I think that there's a lot of very interesting issues here. Like a feature that we wanted had been conditioned on a capability or a design decision that was made very early in our project. So we don't know what those are years later, but that's something that is a risk to all ongoing projects when you think about, oh, maybe we can add this functionality somewhere later on. So also is that terrain traversability is a keystone capability. You need to be able to go over any types of terrain. And the larger the window or the aperture of the type of terrain you can go over, the more likely you are to be successful. That remains to be a challenge today, I would argue. And unless you have a very intertwined design of your robot platform with the control mechanisms that are underlying it, you can essentially fail in this place and then have a catastrophic catastrophic event, which is why autonomy is, I think, one of the harder problems still conditioned on that. So speaking of sensors, I want to talk a little bit about our sensor head. This was every team came up with some different type of perfect design sensor head, and yet all of them ended up being very similar to this one, which was 3 Gig-E cameras, maybe 4 Gig-E cameras, and an ouster or some other kind of automotive-grade lidar, and then some illumination in order to look around and have those cameras actually be able to look at something. In this case, we also added a flash lidar for terrain classification capabilities, but we could have conceivably done that with our automotive-grade lidar. We used an IMU, Parker IMU GX515. Many of you have probably used it before. and actually, I need to credit CSIRO's Matt Hudson with the idea of using gigi cameras as the solution to USB vision. I think that was a really, I mean, that was one of those cross-germination of ideas that happened because we were all in the same area. All right, so that's all for platforms. I think that there's a lot more that I could go into on that, but for sake of time, let's talk about mission management, this human-robot interaction component, where I think there still exists a big challenge for us. The mission was managed by a single human supervisor, as I mentioned before. I think we really lucked out to have an active Air Force colonel on our team, was fighting or flying fighter jets, actually like somebody who had to work under stress in many different systems and signals that they would have to be prioritizing between. So that PhD student was Dan Riley. He earned his PhD last year with Eric Frew. He was our sole human supervisor and took charge of tasks from managing artifact reporting to DARPA to redirecting robots, even directly teleoperating the robots with those game pads that I had shown previously. You'll see here the orange areas in the status bars during the final event run where Dan had to directly interface with the robot in order to do something, override the autonomy in most cases. For those in the know, I kind of want to show these statistics in a meaningful way. What does it mean to do autonomy in these kinds of environments? Typically, we look at what the percentage in green is, which is like how frequently somebody had to, like our system in perfect operation, someone could do nothing and just watch it evolve. That was 52% of the time. And the mean time in green, or the number of minutes that would go by where a robot, where the full system would need no interaction, was 3.5 minutes. So that means that on average, 3.5 minutes would go by without any sort of event occurring. And why are these statistics important? Why do I focus on these? It's because if you have too frequent of interactions, or this mean time in green is too short, let's say 1 minute, that means that on average, the human supervisor will have to actually interface with the system in order to fix it like every minute, which means they either solve the problem in a minute or they have a consistently increasing backlog of problems that they have to deal with. Many of our co-competitors had that issue, where they would say, oh, the human supervisor is going to take more responsibilities. I'll just try to put that into context. That was about 9 minutes per robot, which means that for each robot, you could let it run for 9 minutes without there being an issue, which I think is a pretty good, actually really good compared to some of the other settings that I've seen for field robotics. And this is just one quick overview, and this is explained, I suppose, in better detail in our journal paper. But where did we explore and not explore? We actually didn't explore a lot. So only the deep shaded places in this map are the places where we actually went. And you can see that that's not the entire map. In fact, we missed this entire unexplored cave in the back that I had shown the picture of before. And yet we still scored third. Maybe that's a lesson to take away, but let's talk about that in a second. So to close this out, I want to just give some, I think, my pieces of advice for people that are thinking, robots are the future, let's go ahead and try deploying these out in the real world. I think that there's a multifaceted and delicate balance between validating and practicing and developing. And by that I mean it's not a simple trade-off for time, okay? It's not every minute that you're doing testing or some sort of practice that you're not developing, right? I mean, there's two separate ways that you can spend your time. How should you spend it? It's actually that what I mean by delicate balance, it's that for every minute that you're doing some validation of a system, you're paying into a pocket of time you're going to have to also pay again in order to validate the new system if you innovate on it. By that I mean, like, you will end up with this system that looks like a NASA launch, right? I mean, like, it's essentially every system that is flight approved is the one that we're going to go with. And if you want to go and do something different than a previously flown component, then you're going to have to do n hours of testing on it, where n is equal to the number of hours that have already gone into the previous component. It's kind of difficult to do. So it makes our team look very much less and less like a scrappy, innovative project, right? For every new thing that's been tested, you say, oh, I don't want to touch that next time. So the final 1% of errors in our system, I would say also, without proof, that they were Poisson distributed in occurrence. They could end a mission at any minute, right? So if you wanted to have any sort of change, it would really have to be something that you were getting good statistics on for failure. OK, the next one was buying versus building. This is like a constant IT conversation. Like, should I build my own email server, or should I just pay Gmail to do it for me? So partners that brought technology, like Boston Dynamics or Meshmerize, they were very beneficial. But if we ended up going to some outsourced industry for saying, oh, please solve the problem for us, we actually had a couple of components that were we tried using consultants for, or even small businesses. We ended up just not being able to integrate it. And it's because if we needed some change, we would have had to go back to them, have them change it, or we would have had to master their system afterwards. This is a real problem. So there's a bit of a nuance there. I'll say a foundation for autonomy is still definitely missing. Maybe at this point in the talk you're already familiar with this and you believe me. But industry is still seeking a total solution. We have no really well-established framework for getting to the level of reliability that I think is necessary. And even as recently as last week with this DARPA Racer project, there's this startup that started out by a professor at University of Washington called Overland AI. It's hoping to solve the problem. I think that there's going to be many startups like this that have to be trying to solve this general foundation for autonomy before we finally can see it in many applications. And the last thing that I'll mention, which might be something that the business folks among us might already kind of really appreciate, but I think was a news for us, was personnel and project management is sometimes, I would argue maybe very frequently, more important than the sort of deep tech innovation that you're thinking you're bringing to the table. We had some really deep tech innovations we wanted to show off at the DARPA Subterranean challenge. And yet, the thing I think that really stopped us from being successful was being able to have scientists and engineers with project oversight that felt like they were actually empowered to make decisions because they were there having conversations daily with the people that were trying to solve deep problems. So I think that that's the last thing that I'll mention there. So moving away from this pontification about what we learned, I think that there's something to be said about what didn't we learn. And so there was this the conclusion of the final event, there's this PI roundtable. Here's the program manager, Tim Chang, asking all the PIs, which part of this problem are solved? And many areas during that roundtable were asserted to have been solved that I think I take explicit exception to. I mean, obviously I would agree with some of the sentiments, but I want to just zoom out a little bit and say, the robot stands here. So let's see if we can get this video going. The robot stands here for over 2 minutes. It may be waiting for human input. Maybe it's calculating a plan. Maybe it's trying to resolve a perception issue, like calculating a loop closure. Either way, it's wasting precious time. And I don't think that agility in this context is solved in any definition of the phrase, right? I mean, if we can have a robot sitting in a spot for 2 minutes, that's equivalent to a human sitting in a spot for 2 minutes trying to figure out what they should do next. I think that's problematic. I don't think that we're anywhere near human capability. This was the first place team, right? During the final run. So I think there's something to be said about that. I would say that environmental disturbances aren't solved. This is the second place team, Data 61 CSIRO. You can see a bunch of graduate students. Oh no, they have to rebuild that quadrotor overnight. It's not easy. Now DARPA did replace that piece of paper afterwards, just so that it was fair. And I'm not going to only claim the other teams had all the problems. I mean, we had plenty of problems. Here's our robot standing there for a while, and then trying to figure out how it can move around. What is it doing? I mean, this is just so frustrating to see as a roboticist with an autonomy focus on it. And then, and then out of commission. So anything can happen, right? I think that there's so many problems that are still unsolved. I would go so far as to say anecdotes aren't the only thing that I can bring to bear for this argument. Is this a solved problem? These are the top scoring teams. Here we are, Marble, number 18. Cerberus and Data 61 or CSIRO are tied at 23, but this is out of 40. So we found 23 out of 40 of the people that could have potentially been saved, or 23 out of 40 of the structural defects, or 23 out of 40 of the, I don't know, some kind of threat, what have you. I don't think this is solved in any definition. I think we did a great job. I'm not minimizing the effort. I am merely saying there's a lot further to go before we have any confidence in fielding any one of these systems. And now I'm going to switch gears. So if you were hoping to learn something new about a technology that my group specifically has developed, now's the time. Here we're going to talk about, I want to deep dive on one type of problem we saw as unsolved during the Subterranean challenge, which was navigating in these sorts of visually degraded environments. or VDEs, such as like smoke, fog, other sort of like challenges where something is swept up and you can no longer navigate because your near vision or vision-based sensor has failed for some reason. And just to explain what's going on the left here is a front-facing view of what even very light fog looks like when you have active illumination in the setting. I know it's pixelated. This was the view that the Human Supervisor had when he was trying to teleop the robot through this fog here. And on the right is a view of what the lidar-based occupancy map sees after fog enters the area. And what you'll see is this sort of like spectral figure sort of sitting in the way and probably stopping the robot from moving any further. So that's essentially a failure for planning and everything else down the stack. There are very few perception systems that are designed for less than optimal conditions. None that are naturally suited to handle a broad range of perceptual challenges like haze and particle obscurance. That's what octomaps look like when you have fog and lidar-based mapping going on in tandem. And on the right is just a camera, so you can see that it's a pretty good amount of fog, but you could probably navigate in it, right? So we can see the state estimates also here from visual inertial becoming much less accurate due to fog. So I think that there's a lot to be said here. These visual challenges resulting from the environment aren't the only problem. We also have other areas where we have if we have active illumination, we have illumination drop-off because the light only goes so far. Bad exposure because we end up having close-in objects have stronger artificial light attached to them, and therefore ones further away end up being not seen. There's a balance of normal auto exposure settings, but still a really big problem. Here we have motion blur because just generally it's low illumination. That'll cause a problem when it comes to state estimation or mapping. And specular highlights, so anything, if you have this active illumination, anything that's reflective is going to come up like way overexposing the image. And so these are all issues associated with these visual degraded environments. Some of them also affecting LiDAR, but not all of them. So my suggestion was that we should maybe look at radar. So new developments, many people have sort of not looked at radar for a long time. I ran a workshop at ICRA a year and a half ago, and it was on visually degraded environments, perception in VDEs. And in that case, pretty much all of the great experts that we had come together on said that radar was nowhere near prime time, which I believe and I agree with. I think that there's a lot more work to be done here. And what I think is most often forgotten is that while we're here developing algorithms, other people are out developing new sensors. And in this case, sensor fabrication has resulted in a very small radar sensor as an option. So I'm showing that here, and I show it with a banana for scale. Radar, as you know, provides detection and ranging information, just like any normal radar, similar to LiDAR. But in the millimeter wave case, the frequency of the EM waves emitted from the sensor are 4 orders of magnitude lower than that in the visual realm, meaning we can see refraction of the wave on matter with a characteristic length of about 4 times larger, okay? Which means that in this case, we actually can penetrate most types of hazed dust, and unfortunately it also means that we have low spatial resolution and that some things that would normally be highly reflective for light become completely transparent to radar. And so this complicates the story a lot. Here we see aligned radar and LiDAR data from a sensor rig being hand-carried through a parking garage, and radar targets are represented as red points, LiDAR points are green, and the sensor rig's pose is marked by that RGB axis in the middle. It becomes pretty apparent that the radar scans are very different from LiDAR scans. First of all, they're much more sparse. There are only 200 targets returned per scan versus LiDAR, which is in tens of thousands. In addition, there's very little repeatability from scan to scan. Returns are there, the next scan they're not, the next scan they're there. And the radar sensor may detect targets on the ceilings, beams, cars, or pillars, but it might not actually be able to figure out where is the ground. And there's a high number of false positives, but there's also, unfortunately, a large number of false negatives. This should demonstrate some difficulty in using radar, hopefully. Previous methods have been explored in this, like we have pictured here, this radar-based state estimation system that is put atop an autonomous vehicle by Oxbotica. They're using this so-called NavTech radar. It's mostly a 2D environment, so they use this power-hungry radar sensor that is pretty heavy as well. It's 6 kilograms with 30-watt power draw. And it doesn't really make those methods very suitable for small, agile robots. The radar returns from a sensor like this look very different from the imaging radar that I showed, or automotive-grade radar that I showed in the last one. What we're interested in is using this type of radar for this kind of application, where we want to be able to fly a UAV with this radar attached to it. So hopefully, we can carry this with an MAV pretty easily. Now, in order to do this, I'm going to go over a couple of radar basics and then conclude with discussing where we've taken this and maybe some next steps for you if you're interested. So our radar system returns targets parameterized by range, Doppler velocity, and azimuth and elevation angles, like pictured here. And so those Doppler measurements are basically projecting a vector from the sensor velocity and relative velocity along the ray between the sensor and the point itself. All right, so if we assume the sensor platform is moving and all of the other objects in the scene are stationary, then the velocity of the objects in the scene relative to the sensor has equal magnitude but opposite direction of the velocity of this platform. So in this case, if we have Doppler measurements of many objects distributed throughout the scene, we can actually regress the velocity of the sensor platform itself using this kind of constellation approach that I extend based on one return. So what we did was we came up with essentially a Doppler observation model for velocity. It's the true radial velocity of the target is the dot product of the local frame velocity of the sensor and the unit ray between the sensor and the target. It's possible to use this model alone to estimate the sensor platform's local frame velocity, but there's a large amount of noise in the Doppler measurements, which makes estimation from Doppler errors alone unreliable. And so what we do is we actually decide what we're going to jointly estimate the system's state's velocity over several time steps, also using an inertial measurement unit in order to correct or provide sort of short-term spatiotemporal constraints here. This is shown in this factor graph, wherein we connect Doppler targets to individual states, in this case velocities of the robot, and then we use these binary constraints in change of those velocities as the IMU factors here. So if we want to be able to set up our full state vector, that is actually just the velocity of the robot, or in this case just the radar, the quaternion orientation of the radar rig, and then also the biases on the accelerometer and gyroscope in order to accurately forecast or estimate what the motion of the platform is. And so as one normally does with these sort of factor graph formulations, one can set up an optimization term by which they weight the Doppler term and the inertial term in order to come up with some sort of minimization on a residual of what these errors are. All right. So for state estimation, we actually used a refinement on that method. The biggest change is that we estimate velocities in the global frame rather than the sensor frame. That helps us in the ability for us to sort of paste in what external measurements would look like, including those octomap measurements. So here we're no longer estimating what the velocity of the sensor is, but now the velocity in the world frame, and also what the rotation is from the world frame to the sensor frame. Notice that required this one tiny change in this term. And we also have expanded on that in a later paper, this ICRA 2021 Radar and Robotics Workshop, wherein we are also doing marginalization over a sliding window of measurements. And what does this look like in terms of the optimization? It's actually just a very small modification of the Doppler term, and essentially just doing this in world coordinates. Now, what does this look like from this error? If I wanted to fully expand out what this error looks like, I have to include this world to sensor rotation as well as the world frame velocity. So that's essentially the one modification where now we're measuring the rate of sensor to target and error and ray measurement just with respect to the sensor previously. It's no big change there. Okay. So this is why the Doppler error term now includes the error in the target ray in addition to the Doppler measurement error. This is because, unlike LiDAR, there are likely to be significant errors in the target ray, where that ray is actually coming from. Because we actually weren't sure, like in a LiDAR, we know exactly where the LiDAR beam is going out to. But in this case, there might be errors actually in where the return is coming from, because there may be some sort of discretization along the ray that is coming up with, oh, this error is coming up from this particular point, except like slightly offset from it. So this is taken into account in the error in radial velocity measurement and the error in the ray measurement here. In the end, what does this look like? Well, we get a couple of cool results. First of all, we can now fly a quadrotor independently of any other sensor using only a millimeter wave radar and an IMU. It doesn't look like it's flying just yet, so how about we give it a little, OK. So here it'll be able to do a little bit of station keeping with some drift, but this is only using the IMU and the Doppler velocity term, which is pretty incredible. We can also do sparse mapping, like I had mentioned previously. We would like to be able to paste those different returns from radar into the world frame. That requires us actually estimating where the robot is with respect to the world frame. And we can do that just as in here, but we notice one other problem. And just briefly, this problem essentially arises from the fact that we can't have very high reliability on any of the points that we have. So what we do in this case is we, anyone else know where we're going with this? Basically run it through a filter that's based on a point-to-point, is this an inlier or outlier detection with lidar supervision, based entirely on PointNet++, the segmentation network version of that. And the result here is that we can use this lidar supervisory signal, which is essentially like, is there a radar point within k centimeters, really, of a lidar point? If so, that's an inlier. Otherwise, it's an outlier. We can use this to train some sort of outlier rejection framework. And then in the end, what we get is a fairly nice, like, dense map of this world, volumetric map of this world. And so this is using those trained inlier filters from lidar supervision with Octomap in order to build what's essentially a dense map of the environment using radar only, because there's no lidar at the time of inference. And I'll go even so far as to say we built this completely together using our state estimation pipeline and our mapping pipeline, as previously discussed, in order to come up with, like, how does this work if I were trying to just navigate in this hallway? And the results are pretty good. They're not exactly dense maps, I would say. But in the end, we can use this in order to sort of build a primitive planner. In this case, this primitive planner is given here as these arrows that are coming from the platform, the rig of the platform. And if there's a wall nearby, then it would say, oh, don't go that way. This is still, like, I would say a pretty noisy planner. But in many environments, it could be potentially useful. Especially if we have no other sensor mechanism to rely on. So one last pitch. It's that we decided to build a data set based on these data that have multiple entry points. All we've shown today is all those different radar returns, those detections. But there's actually a high depth of data that is beyond that, because radar is a fairly complicated sensor. We can actually look at what the raw returns in complex value space are from each one of these virtual antennas on this array. And that gives rise to, I think, a lot of opportunity for machine learning on raw radar signals that has not yet been explored. The data set is fairly diverse. It's indoors, like in the engineering center here at CU. It's outdoors, based on this one of my students riding one of those electric skateboards with the rig and going down the Boulder Creek path, really fun. And then, of course, we had to do it in a couple mines, so we have some mine data sets there. And here are some initial results of using our own raw fast Fourier transform processing on the raw IQ values from this imaging radar rig. So with that, I know I'm out of time. So I want to thank you for listening, for your attention. I want to thank my research group and all my sponsors. And with that, I'm happy to take questions.
Yeah, thank you, Chris, for a great talk, and also for sharing some of the lessons learned. Certainly resonate with many of the statements that he made, in particular regarding personal and project management, that oftentimes is not really properly taken into account when you think very hard about the technological side of autonomy. But when you try to field something, and I can tell you, based on my experience at NVIDIA, then project management is a really big deal. Anyways, that said, any questions? Yeah.
Yeah, so I was just wondering, I guess, like how you would handle like dynamic objects, or if you would have to somehow like be able to like filter those out when you're trying to use the like Doppler model.
Great question. So actually, something I didn't mention is that we use a variant of ransack in order to figure out which returns might be a result of some dynamic object or a dynamic return. RANSAC is essentially a way of determining what of your set is an outlier and then just completely removing those from the estimation set. It's not exactly a fast method, and the method that we use is slightly faster, called MOESAC, wherein we're trying to basically come up with a hypothesis for what is an inlier versus an outlier by taking smaller samples than RANSAC might normally come up with, essentially. Great question. Because they would definitely mess you up. Other questions?
So great talk. You mentioned at some point of the talk that in the DARPA challenge, the operator was sometime was teleoperating some of the
Yes.
robots used.
Yes.
So I'd like to know what kind of framework did you follow in order to say, okay, this task should be automated and this task should be teleoperated?
Great question. So we did not have a great identifier for when something should be teleoperated or not. We could rely on not having a heuristic for determining that, like flagging the human's attention, because of, I think, two factors. One, we had pretty good autonomy, as I mentioned, I would argue. Pretty good being obviously very far away from what I would consider to be fieldable, but still good enough such that a few minutes could go by without a human intervention even being required. On the other hand, we also had a great human supervisor who would be able to identify where faults in the system might occur and then predict them and then stop them. The thing that I think was most important from our autonomy stack was our ability to not get stuck on terrain. Because if that happened, that was essentially the most fatal occurrence that would happen to a robot. It doesn't matter if you can teleop after that. So what we did was we built ourselves around a case in which essentially we wouldn't have robots run into one another and they wouldn't get stuck on terrain. After that, what we would get from autonomy is potentially suboptimal behavior, at which point the human could sort of break it out of that suboptimality as a result of whatever it might be. Hopefully that's an answer to you. I think there's a lot of good research that could be coming up from that, though.
In the score, was there an explicit penalty for human intervention?
No. No. The only thing that mattered for a score was how many artifacts you got within some number of meters radius of the true artifact location, which was surveyed in using surveying data. So the human could do whatever they liked, but as you can imagine, a human only teleoperating a single robot wouldn't score that many points.
Sure.
And so that was sort of the balance that had to be struck. It was maximized along that frontier.
I have a question regarding your radar sensor data. So you had like a method to basically supervise like the radar signals with the lidar signals. How much, like what percentage is it, for instance, like per radar, like the sensor itself, and how much it is sort of generalizable across different sensors?
Great question. We didn't really explore that. We looked at a particular radar sensor in 1843, AWR 1843. I imagine it would probably generalize well across other sensors like 1443s, but maybe not two-dimensional sensors like 1642s. These are different model numbers in TI. I think that I personally believe it would go very well actually in any 3D imaging radar. Because what we're learning is that there are certain points that are reliable with respect to LiDAR, right? So if you decide to add more points onto that, then we should be able to see similar types of performance. Most automotive-grade radar sensors that I've seen since the development of this particular sensor have essentially increased the number of points that can be returned from the sensor as well as their resolution. I don't think either of those would be necessarily affected by using this particular method. At the same time, it didn't require that much data to do this supervision, so I wouldn't be too concerned if one had to collect one's own data set and then do that training themselves. Great question.
Are there any questions from the chat?
Nope, not so far.
I'm curious, what do you see as the future of this sub-T challenge? You know, after the DARPA challenge, there was a DARPA urban challenge, and then a number of startups.
So DARPA has another challenge out right now. I don't know if you know that.
Okay.
It's currently under the proposal stage is finished just as earlier this week. It's called the DARPA Triage Challenge. I think that's one example. But another one is if it's not quite a challenge, but it's another program that I just mentioned, which is that RACER program. As far as I know, there are 3 major teams in that program, and one of them just spun off a startup. I wouldn't be surprised if I see some other startups coming out from that. That's essentially gauged or aimed at trying to develop autonomy capabilities for the robot combat vehicle for the Army, is what I can see. Very, very interesting challenge. Essentially, they are putting a Polaris. Anyone know what a Polaris Razor is? These things are crazy. It's essentially an independent suspension dune buggy with like a Honda Civic engine on it. So it's like a lot of power, turbocharged, and they're trying to make those autonomous. So it's like true off-road autonomy. Really, really interesting program.
Cool. Any other questions? All right, so let's wrap up. Thank you again.
Thank you.